Welcome to today's session. In this video, we'll tackle problem number 418, titled Sentence Screen Fitting. This problem challenges us to fit a given sentence repeatedly onto a screen of specific dimensions, row by row. We'll explore different approaches, break down the complexities, and learn valuable insights. Let's get started. Imagine you are given a screen with a specific number of rows and columns, and you want to repeatedly display a sentence on it. The sentence is provided as an array of words, and your goal is to determine how many times the entire sentence can fit on the screen. There are a few constraints. The sentence must be displayed in order, you cannot split a word across two lines, and words are separated by a single space. Additionally, it's okay if a line ends with extra spaces. Once you reach the end of the sentence, you simply start displaying it again from the beginning. For example, if the sentence is, "Hello, world," the screen is 2 rows and 8 columns. Your task is to figure out how many complete times you can display the sentence within these dimensions. The output for this problem is an integer that represents how many times the entire sentence fits on the screen. Let's look at some examples to clarify. In the first example, the input sentence is, "Hello, world," with 2 rows and 8 columns. The output is 1 because the sentence can be displayed fully once within these dimensions. Now, we will break down how this happens to better understand the process. Starting with the first row, we can fit the word hello followed by a space. This leaves 2 columns unused, so the row looks like hello. Moving to the second row, we fit the word world. This row also leaves some extra space, but the sentence is displayed in its entirety. Since we reach the end of the sentence and there is no more space to start it again, the sentence is displayed exactly once. Another example uses the sentence, A, B, C, D, E, with 3 rows and 6 columns. The output here is 2 because the sentence can fit twice. Let's break down the rows to see how. In the first row, we can fit a BCD, leaving 1 column unused, so the row looks like a BCD. In the second row, we fit EA, leaving 2 columns unused, resulting in EA. Finally, in the third row, we fit BCDE, which uses all columns perfectly. The sentence is displayed twice in total. Now consider another example with the sentence, I had apple pie, 4 rows and 5 columns. The output in this case is 1, as the sentence can only be displayed fully once. Let's see how the rows are arranged in this example. In the first row, we fit I had, using all 5 columns. The row looks like I had. On the second row, we fit apple, again perfectly using all columns. The row looks like apple. In the third row, we fit pie, leaving 1 column unused. The row looks like pie. Since there is no room to start the sentence again on the fourth row, the sentence is displayed exactly once. Now, let's review the constraints. The sentence will include between 1 and 100 words, each with a length between 1 and 10 characters. The number of rows and columns can be very large, up to 20,000. Edge cases include very small screens, sentences with words too long to fit in the column width, and situations where rows or columns are extremely large. These constraints and edge cases ensure that the solution must be efficient and handle a variety of scenarios effectively. To tackle the problem of sentence screen fitting, we first consider a brute force approach. The intuition here is to simulate the filling of the screen row by row. Starting from the first row, we fit as many words as possible without exceeding the column limit. If a word doesn't completely fit in the current row, we simply move it to the next row and continue. As we fill rows, we keep track of how many times the entire sentence has been fully repeated on the screen. The steps are straightforward: iterate through each row, fit as many words as you can within the column constraints, and ensure no word is split. While this approach is simple and easy to understand, its time complexity depends on the number of rows, columns, and the average word length, making it rows * calls /average _word _length, and it requires constant space. This simplicity, however, comes with some inefficiencies that we'll address next. The brute force approach, while intuitive, has some critical limitations. It explicitly simulates every row, which can be inefficient, especially when dealing with large values for rows and columns. Additionally, calculating the fit for each row repeatedly introduces redundancy. To overcome these inefficiencies, we turn to an optimized approach that leverages string simulation. The key idea is to treat the entire screen as a single, long string of size rows multiplied by columns. By concatenating all the words in the sentence with spaces, we can slide through this virtual string to determine how many complete sentences fit. This process involves using a pointer to track the current position in the concatenated string and simulating the screen by advancing the pointer row by row. If the pointer lands on a space, we simply move it forward. If it lands in the middle of a word, we backtrack to the start of the word. This ensures that no word is split while efficiently counting the number of complete sentences that fit. The optimized approach offers significant improvements in both time and space complexity. Its time complexity is O, rows plus n, where n is the length of the concatenated sentence string, and it uses O, n, space to store this string. One of the major advantages of this method is that it avoids redundant computations by treating the screen as a single virtual string, rather than simulating each row individually. This makes it highly efficient, even for large screens with many rows and columns. Another key aspect of this approach is the backtracking mechanism, which ensures that no word is split as we slide through the string. By avoiding unnecessary calculations and leveraging this sliding mechanism, we can compute the fit quickly and effectively. The main realization here is that by stepping away from a row-by-row simulation and treating the screen as a whole, we achieve both efficiency and clarity in our solution. Given these considerations, the optimized string simulation approach is the preferred strategy for solving this problem. It stands out for its balance between efficiency and correctness, avoiding redundant calculations while ensuring that no words are split. On the other hand, the brute force approach, though easy to implement and intuitive, is not suitable for large inputs due to its inefficiency. When comparing the two, the brute force method is straightforward but computationally expensive, while the optimized approach is slightly more complex to implement but highly efficient. This trade-off makes the optimized solution the ideal choice, as it strikes the right balance between clarity and performance, ensuring that the problem is solved effectively even for large inputs. In this problem, we are tasked with determining how many rows of text we can fit into a screen with a fixed number of rows and columns. The input includes a list of words, and the goal is to arrange as many words as possible, row by row, without exceeding the column limit. To approach this, we can start with a brute force solution. First, we initialize some key variables, a pointer to the current word in the list, a counter to track the current row, and a variable to manage the remaining column space in the row. These variables will help us simulate the process of placing words on the screen. Now, we simulate the row filling process. For each row, we iterate through the word list and check if the current word can fit into the available space. If it fits, we add it to the row, subtracting its length plus 1 for the space, and then move to the next word, cycling back to the start of the list if necessary. If the word doesn't fit, we move to the next row and reset the available column space. There are also a few important edge cases to handle. For instance, if a single word is longer than the total column width, the problem is unsolvable. Additionally, if we run out of rows before all words are placed, we stop the simulation. Finally, we track how many complete cycles of the word list occur, as each cycle represents the entire word list being written once. A key insight here is that the placement of words follows a cyclic pattern. Once the pointer reaches the end of the word list, it wraps back to the beginning, and this repetition allows us to identify potential optimization opportunities. For example, instead of simulating the placement row by row, we can pre-compute how many words fit into a single row and use this to efficiently calculate the total rows required. It's also important to account for critical edge cases, such as words that are too long for a single row or rows that remain partially filled due to insufficient space. Recognizing these patterns and edge cases is essential for improving the efficiency of the algorithm. To implement this solution, we rely on a few key data structures. The word list itself stores all the words that need to be placed on the screen and provides access to their lengths during the placement process. Counters such as the current row, remaining columns, and a pointer to the current word help track the row filling progress. Additionally, a cycle tracker is used to count how many full passes through the word list have been completed. These components work together to simulate the row-by-row placement and ensure we can efficiently manage the word list in rows. Analyzing the brute force approach, we observe that the time complexity is tied to the total rows and the number of words. In the worst-case scenario, this results in a complexity of O, total_rows*len, words. On the other hand, the space complexity is minimal, as we only use a few counters and pointers, giving us 1 space usage. To optimize this, we can pre-compute how many words fit in a single row and use this information to skip redundant calculations. Modular arithmetic can further enhance efficiency when handling word list cycles, allowing us to reduce unnecessary iterations and streamline the overall process. This solution determines how many times the given sentence can fit into the screen within the constraints of the rows and columns. The core idea is to simulate the placement of words onto the screen by treating the sentence as a repeated string. First, the elements of the sentence are joined into a single string separated by spaces, and an extra space is appended to simplify word wrapping. The total number of characters that can fit in the screen is tracked by the variable total_chars. For each row, we add the number of columns to total_chars, which simulates filling the row completely. If the character at total_chars %sentence_len position in the repeated sentence string is a space, it means the row ends neatly, and we skip over the space. However, if a row ends in the middle of a word, we adjust total_chars backward until it aligns with the start of the next word. Finally, the total number of times the sentence fits into the screen is calculated as total_chars / sentence_len, which gives the number of complete repetitions of the sentence within the total characters fitted on the screen. This approach ensures efficient computation, as each row is processed in constant time, making the algorithm run in rows plus calls time complexity. Here, we're implementing a solution to fit a given sentence onto a screen with a specific number of rows and columns. The first step is to join all the words in the sentence into a single string, separated by spaces, and append a trailing space at the end. This ensures smooth wrapping when iterating through the string. We then calculate the length of this combined string, which will help us track the wrapping point. Next, we initialize a variable, total characters, to keep track of the total number of characters that can fit across the rows of the screen. Now, we loop through each row. For each iteration, we add the number of columns to total characters, assuming we're allocating space for that row. However, we need to ensure that word boundaries are respected. If adding columns places us at a space, we can seamlessly wrap to the next word by incrementing total characters. If the current position happens to be in the middle of a word, we use a while loop to backtrack to the start of that word by decrementing total characters until we hit a space. Finally, once we've processed all rows, we calculate how many full repetitions of the sentence fit on the screen. This is done by dividing total characters by the length of the combined sentence string, which gives us the total number of times the sentence can be displayed completely. The method then returns this value as the result, completing our implementation. This approach ensures we handle word wrapping and row constraints efficiently, while leveraging modular arithmetic to manage the circular nature of the sentence string. To solve this problem, we start with the basic example where the sentence is, "Hello, world," the screen has 2 rows, and each row has 8 columns. First, we initialize a few values. We create a single string, sentence_str, by joining the words with spaces and adding a trailing space, resulting in "Hello world." The total length of this string is 12, stored in sentence_len. We also initialize total_chars to 0, which will keep track of the total number of characters we can fit on the screen. For row 1, we add the column count, which is 8, to total_chars, making it 8. However, the character at position 8%12 in sentence_str is r, which is not a space. This means the row ends in the middle of a word, so we need to adjust backward until we land on a space. After the adjustment, total_chars becomes 6, ensuring the row ends cleanly after the word hello. For row 2, we again add the column count of 8 to total_chars, bringing it to 14. At this point, 14%12 gives an index of 2 in sentence_str, which corresponds to the character D. Since this is not a space, we adjust backward until total_chars lands on a space. After adjusting, total_chars becomes 12. Now that all rows are processed, the total number of characters that fit on the screen is 12. To calculate the number of full sentence fits, we divide total_chars by sentence_len, which is 12 //12, giving the result of 1. This means the sentence can fit exactly once on the screen. In the next example, the sentence is, B, C, D, E, and the screen has 3 rows with 6 columns. We start by initializing sentence underscore str as a bcde, with a length of 8 stored in sentence underscore len. Total underscore chars is initialized to 0. For row 1, we add the column count of 6 to total underscore chars, making it 6. At this point, 6% 8 gives the index of 6 in sentence underscore str, which corresponds to the character e. Since this is not a space, we adjust backward until total underscore chars lands on a space, reducing it to 5. This ensures row 1 ends cleanly after the word bcd. For row 2, we add another 6 to total underscore chars, bringing it to 11. The index 11% 8 corresponds to the character b, which is not a space. Adjusting backward, total underscore chars becomes 10, ensuring row 2 ends after the word e. Next, in row 3, we add another 6 to total underscore chars, making it 16. The index 16% 8 corresponds to the character e, which again is not a space. Adjusting backward, total underscore chars becomes 15. After processing all rows, the total number of characters that fit is 15. Dividing this by sentence underscore len, 15//8 results in 1, meaning the sentence fits completely once on the screen. Now for a case where the sentence is, I had apple pie, the screen has 4 rows and each row has 5 columns. We start with sentence underscore str as I had apple pie, which has a length of 18 stored in sentence underscore len. We initialize total underscore chars to 0. For row 1, we add 5 to total underscore chars, making it 5. The index 5% 18 corresponds to the character a, which is not a space. Adjusting backward, total underscore chars becomes 4, ensuring the row ends after the word I. For row 2, adding 5 to total underscore chars brings it to 9. The character at 9% 18 is p, which is not a space. After adjusting backward, total underscore chars becomes 8. For row 3, we add 5 again, making it 13. The character at 13% 18 is also p, so we adjust backward, reducing total underscore chars to 12. Finally, in row 4, we add 5 to get 17. The character at 17% 18 is p, and adjusting backward leaves total underscore chars at 16. After all rows, the total number of characters is 16. Dividing this by sentence underscore len, 16//18 gives 0. This means the sentence does not fit fully on the screen even once. To analyze the time complexity of our solution, we start by breaking the process into its key components. First, we pre-process the input sentence by joining all the words into a single string called sentence underscore str. This step has a time complexity of O(n), where n represents the total number of characters in the original sentence, including spaces. Calculating the length of this string, sentence underscore len, is a simple O(1) operation. Next, we iterate through the rows of the screen. For each row, we add the column count, calls, to a running total of characters, which is an O(1) operation. We then check whether the current position in sentence underscore str aligns with a space, which is also O(1). However, if the position falls in the middle of a word, we adjust it backward to align with the start of the word. This adjustment occurs within a while loop that, in the worst case, traverses the length of the longest word in the sentence, denoted by W. This means that the worst-case time complexity for processing a single row includes an O(W) adjustment step. Since the cost per row in the worst case is O(W), the total cost for processing all rows becomes O(rows*W). After iterating through the rows, we compute how many times the sentence can fit on the screen by performing a division operation, total underscore chars / sentence underscore len, which is O(1). To summarize, the overall time complexity depends on the number of rows, the maximum word length, and the total number of characters in the sentence. In the best-case scenario, where no adjustments are needed in the while loop, the time complexity is O(rows). In the worst-case scenario, where adjustments are required for every row, the time complexity increases to O(rows*W). This difference highlights how the structure and alignment of words in the sentence can influence the performance of the algorithm. Now turning to space complexity, the primary factor is the storage of the sentence underscore str. This string is constructed by joining the words in the sentence and appending a space, so its size is proportional to the total number of characters in the sentence, including spaces. This requires n space, where n is the total size of the sentence. Beyond this, the algorithm uses a few scalar variables, such as sentence_len, total_chars, and loop indices. These variables require constant space, denoted as O1. Importantly, the solution does not rely on additional data structures or recursive calls, meaning there is no extra space overhead beyond the storage of the sentence_str. Therefore, the overall space complexity of the solution is O(n), making it efficient in terms of memory usage. Comparing this approach to a naive solution helps illustrate its efficiency. A brute force method would simulate the sentence fitting process character by character for every cell in the grid, resulting in a time complexity of rows * calls. This is because each row and column combination would need to be processed individually. The space complexity of the naive approach remains O(n), since it also involves storing the sentence. The optimized solution, however, uses modular arithmetic and skips unnecessary character-by-character checks, reducing the time complexity to rows *w in the worst case, which is significantly faster when the number of columns is large relative to the length of the longest word. The space complexity remains O(n), as it is dominated by the storage of the sentence_str. To confirm the time complexity mathematically, note that the while loop inside the row iteration adjusts at most w characters per row, meaning the total adjustment across all rows is bounded by rows *w. Since no additional memory is used beyond the pre-processed string, the space complexity is conclusively O(n). When solving the sentence screen fitting problem, there are several common mistakes to be aware of. First, failing to account for word breaks can lead to errors, especially in cases where a single word exceeds the column width. It's important to ensure that no word is split across rows unless the input explicitly allows it. Next, mismanaging index wraparounds can cause issues when repeatedly iterating through the list of words. Without proper handling of the transition from the last word back to the first, your solution might enter an infinite loop or produce incorrect results. Another frequent error is overcomplicating the row fitting process by simulating each row placement in detail. This can result in unnecessarily high time complexity, which is avoidable with smarter pre-computations. Additionally, ignoring the input constraints, such as assuming that all words individually fit within the column width, can lead to redundant checks and wasted effort. Finally, for large inputs, brute force solutions that simulate every row placement are simply too slow. Scalability is key, so always aim for an optimized approach to handle these scenarios efficiently. Now let's discuss some valuable insights for interviews. Efficient solutions often rely on recognizing patterns in the way words are placed. By identifying repeating sequences, you can avoid redundant computations and significantly speed up your solution. Pre-computations also play a big role here. For instance, calculating in advance how many words fit into each row can eliminate the need to simulate the process row by row. Techniques like modular arithmetic or sliding windows can be particularly helpful. It's also crucial to test edge cases, such as a single long word, a repetitive single short word, or a mix of short and long words. These scenarios help ensure your solution is robust and handles all possibilities. Additionally, while brute force approaches are straightforward to implement, they're rarely acceptable in interviews. Instead, be prepared to discuss alternatives, such as pre-computing word fits or leveraging modular arithmetic. This demonstrates not only your problem-solving skills but also your ability to optimize for efficiency. It's also helpful to explore related problems that build similar skills. For example, the core problem we're discussing here is LeetCode 418, sentence screen fitting. Another relevant challenge is LeetCode 68, text justification, which also involves formatting text but adds constraints around alignment, making it slightly more complex. LeetCode 57, insert interval, may seem different at first glance, but it involves managing ranges efficiently, a useful skill for tackling problems like this. Lastly, LeetCode 1228, missing number in arithmetic progression, focuses on identifying patterns in sequences. While it's not directly related, the ability to spot and work with patterns is a transferable skill that can be valuable for sentence screen fitting and similar problems. Finally, let's consider the alternative approaches and their trade-offs. The brute force simulation method involves placing words row by row and is straightforward to implement, but its O and asterisk rows time complexity makes it inefficient for large inputs. While simple, this approach should generally be avoided in favor of more optimized solutions. Pre-computing word fits is a smarter alternative. By determining in advance how many words can fit starting from each position, you can eliminate redundant computations, reducing the time complexity to O(n). However, this method does require additional memory, so that's a trade-off to consider. The most efficient approach involves combining modular arithmetic with pattern recognition. By identifying repeating sequences in word placement, you can directly compute results without simulating each row. This approach is highly optimized, often achieving O(n), and it demonstrates a strong grasp of algorithmic thinking. While slightly more complex to implement, it's an excellent choice for interviews, as it showcases both efficiency and a deeper understanding of the problem. Great job! We reviewed the sentence screen fitting problem and discussed its solution approach. Remember to practice this and similar problems to solidify your understanding. Thanks for watching, and stay tuned for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!